Or is the Cartesian plane, how many unique things have we used to describe a single point on the Cartesian plane? Two. Yeah, horizontal position and vertical position. Like on planet Earth, we use latitude and longitude. You know, it's the Cartesian plane mapped over a sphere, effectively, right? You have latitude and longitude. You can go to really far decimals to get really exact locations. Are there other ways to label points on a plane? Yeah. Always assume yes in those kind of cases. You know, it's kind of a leading answer. So we have these points right here. On the left, you see X and Y. There are two letters up there that are new-ish to you. What are they? R, and there's another letter up there. What? Theta, right. R and theta right there. R and theta. So another way to describe a point in a plane, R in relation to the point P is what? What does R represent? The magnitude of what, specifically? I like that word, yeah? To the... Yeah, the magnitude of the ray that extends from the origin to the point. So this is the distance from the origin. Now, is R enough to describe that unique point? No. If I just give an R value, how many points does that describe? An infinite number, right? It's actually the definition of a circle. What's the definition of a circle? I understand what you're getting at there, but let's be very careful with our words here. The infinite... You can say infinite, you don't have to say infinite. The collection of all points that are equidistant from one point. Does it have to be the origin? No, you can have a circle centered anywhere, right? So R equals, let's say, 1 would be the circle of radius 1, unit circle centered at the origin. Right, centered at the origin. Okay, so what is theta? We need something else then. What is theta going to be? Theta is what?
The angle.
What angle? Be specific.
The
angle formed, or the angle that extends from what to what? So be more specific, not just the x-axis, the positive x-axis to the ray formed when you connect the origin to the point. You have to be very specific about that because it's not this angle right here, right? It's not that angle. It's the angle formed from the x-axis to the right. And you have to be even more specific than that because, look, theoretically, could I say that? Well, based on what you just said, yeah. So it's the angle formed from the positive x-axis going in the what direction? Counterclockwise direction. We need an orientation. We need a starting ray and an ending ray for an answer, right? So what does that mean? Well, we can just redo the coordinates for points that are things we've worked with a whole lot. So for example, Q. What are these coordinates called, by the way? I didn't actually label them. Polar. Polar. What point is Q in polar form? What's the R value for Q? What's the R value for Q? Take a look up there. 5. What's the angle measure formed between the positive x-axis and, what is it? 0. Hey, what's the Cartesian coordinate for Q? 5, 0. So is it the same? In this case it is. Is it always the same? No. There's an infinite number of points that have the same polar and Cartesian form. What are they? Describe the set for me. Which points? Positive x-axis. Excellent. Is the negative x-axis? No. Because the R is... Can you have a negative R value, by the way?
No.
Actually, you can. You could have a negative R value. What does that mean? You just go in the opposite direction. Like you go to the angle value, and then you go in the opposite direction. It's really annoying. It's annoying. Okay, let's do the fun ones. What about R here? What's R going to be? Well, it's 5 again, right? But what's the angle measure? Use radians. Pi, yeah. Unless otherwise specified, please use radians. Please use radians. Okay, what about V here?
3 pi over 2.
5 comma 3 pi over 2. Yep, that's fine. So now it gets a little bit more fun. What's U? Tell me what U is. Assume it's all integer value 5 again, right? But what's the angle measure? Do you know this exact angle measure? No. Inverse tangent of what?
4 over 3.
Yes, very good. Inverse tangent of 4 over 3. Yeah, it's the inverse tangent of 4 over 3. The angle measure is always going to be the inverse tangent of y over x. Yay. What about P here? What's P? Let's assume that's the point. Let's assume that's the point in Cartesian. Let's assume it's 4, 6 in Cartesian. What is it going to be in polar form? What do you think? What's the distance? Come on.
52.
Square root of 36 plus 16 is 52. Thank you, Ken. Good job. And tan inverse of? Yeah, 3 over 2 or 6 over. I leave it at 6 over 4 just so it's easier to see. Sometimes when you simplify fractions, you make things a lot harder to see. You remember that when we did series, if you had a series not simplified, you could see the pattern. But if I simplified like a couple of the fractions, did it become a lot harder to see the pattern? Like the hint was, oh, if 14 was in all the denominators except 1, make 14 in all the denominators. You remember that. Okay. So what do you see here for these relationships? You've already started using them really. The two straightforward, well, the three of them, or four, I guess you can say this. First of all, what did we use here? The first one we used is right there. R is equal to x squared plus y squared. This is the magnitude using the Pythagorean theorem. And we also know tangent of theta is equal to y over x. So what does theta equal? Tan inverse of y over x. What about x and r? Well, the definition of cosine is x over r, and the definition of sine is y over r. So what does x equal? X cosine theta, and what does y equal? R sine theta. Always remember that. You will use that a lot. Manipulating and working with polar equations is very similar in many functional ways to working with parametric equations. A lot of the manipulation is really straightforward when you see and understand what you're supposed to do. But sometimes, do you remember working with parametrics, and sometimes was it really hard all of a sudden because it was hard to see? Like just because something is relatively straightforward when you do it doesn't mean it's easy to find? No, it doesn't. So what does that mean we can do here? Let's do some fun stuff. So we already kind of did this. So we already kind of did B. We did the polar. Let's go the opposite direction. Let's give the Cartesian coordinates. So for this one right here, if I said P is equal to 7 comma pi over 3, that's a giveaway that that's polar coordinates because there's a radial measure. It doesn't have to be. Theoretically, could that be a Cartesian coordinate? Theoretically? Yeah, it would be kind of weird to write the y coordinate as pi over 3, but it's not impossible. How would you go about writing the Cartesian version of that? Well, you know x is equal to what? What did I say x is equal to? R cosine theta. And what does y equal? R sine theta. Always remember that, right? So if you do this, what's the x coordinate going to be? What's r equal to? There's r, right? And what's that? Theta. So what's the x coordinate? 7 cosine pi over 3. And what's the y coordinate? So yeah, and on a test, if you stop there, would you get full credit? No. You need to know your basic trig values, right? What is cosine of pi over 3? Careful. 1/2. So it's 7 over 2, comma 7 root 3 over 2. Yeah, don't flip them. Careful. Pi over 3 is how many degrees? 60 degrees, so it's the short side, right? Cosine is adjacent, so it's half. However you do it, just know it, okay? Just know it. Okay, so you will need to be able to convert between the two systems. You'll need to be able to convert between the two systems. So what else do we get to do? Well, this is what graph paper looks like in polar land. Instead of the x-axis being down, what is down here? What do you always point it at when you're looking down from a point? What is down? The what? Origin. The origin, yes. The enemy's gate is down. What's that from? I'll give a gold star to anybody who knows this. My last class did not know this, and I was kind of sad. Not like a universe apart, but like the genre is almost right. The enemy's gate is down. You're getting closer. Getting closer.
Star Wars.
Oh no, farther. Nah. Ender's Game. Anybody read Ender's Game?
Oh yeah.
Enemy's gate is down. Come on, I try to like work in pop. Who's read Ender's Game? Like the legitimate read it. It's amazing. The Battle School, Enemy's Gate is down, so you have to reorient yourself here. Now, another way to think about it too is moving side to side in Cartesian land is the same as doing what on polar. If you're moving side, what'd you say? Rotating exactly. So this gives you your first concrete example of things you can do in polar that are much harder to do in Cartesian. So, for example, moving around in a circle, if you had a point in Cartesian and I said rotate it, up until this point, is it really hard to do? It's not straightforward, right? You could do it, right? But you have to use trig and like rotate, keep the distance, right? In polar, is rotating pretty straightforward? Yeah, you just change the theta value, right? So you can do things that you could not do before. You could do things you could not do before as easily. Does that make sense? Everything is relative. So, Example. A. Describe in words the graph of the Cartesian equation y equals 1 and the equation of r equals 1 in polar coordinates. So let's look at r equals 1. What is r equals 1? We already talked about that. If I just said r equals 1, what is it?
It's a circle with radius 1.
Centered at the origin. Yes. You need all of those things to uniquely identify, right? What is y equals 1 in Cartesian? What is it?
Line.
Horizontal line at y equals 1, right? Okay, so those are relatively straightforward to describe in each of their coordinate systems. Okay, write r equals 1 in Cartesian coordinates. Well, r equals 1 in polar, we know it's a circle of radius 1 centered at the origin. What is that in Cartesian coordinates? What is that in Cartesian coordinates? What is it? X squared plus equals 1. We know that. It's relatively straightforward, but is it more complicated than just writing r equals 1? Yeah. Okay, so here's another fun. Try this one for me. So y equals 1. Write that in polar coordinates for me. R, oh, I'm in highlighter mode still. R is equal to cosecant theta. Sound good? Okay, so we haven't really done much calculus. You want to actually do some calculus? Let's see. Should we do some calculus? Let's do some calculus. Okay, so let's take a look at these graphs right here. So these graphs right here, the best way, how many, you've dealt with polar graphs before, right? Did you see them in pre-calculus? Let's just get reacquainted. Put your surfaces, you can put the screens up, get your keyboards, load Desmos, and graph the function on the left, please, on Desmos, please. The area of a sector, this is really important. You need to remember that the area of a sector is 1/2 r squared theta. Where does that come from? Well, if theta is the degree value of the internal angle of the sector right there, how much of the circle is the blue value? Well, that's going to be theta over all the way around. How many radians will go all the way around? 2 pi. So it's theta over 2 pi. That's the ratio of the entire circle. And then what's the area of the circle? Pi r squared, which we proved. Yeah, very cool. Pi's cancel, you get 1/2 r squared theta. That is the area of a sector of a circle. Pretty cool. Yeah. Here's the thing. You can use this now to find the area of polar functions. Because instead of rectangles, what do we now have? We have sectors, sectors, sectors. Because what are you doing? You're sweeping out a sector and sweeping out another sector. What did we add up an infinite number of before? We added up an infinite number of rectangles. That's what we did for Cartesian, right? Dx, and then the height, and then we added up an infinite number of them. But take all the bases and squinch them together, tie them together in a bow at the origin, what do you get? Sectors. You get sectors. Is this a perfect circular sector right here? No, but as they get infinitely small, does the limit of the sum of all of these sectors sum to what you want it to? Yes, the actual one. So all you do is you integrate from the starting angle value to the next angle value of what? 1/2 r squared theta. But theta is not theta here, it's going to be, what's the internal? If you have an infinitely small theta value, what do you call that? D theta. You call that d theta. So what does this look like? It looks like this. If I can get it to scroll, come on. You can do it. Or not. Come on. Let's get it to scroll, there we go. You get this right here. 1/2 alpha to beta of f theta squared d theta. What is f theta? F theta is r. F theta is r. You have r in terms of theta. We are integrating with respect to one variable, so just d theta. So what you do here is add up lots and lots of sectors. So if I wanted the area of this sector right here, just like with parametric equations, the most challenging thing in my opinion is finding the alpha and beta values. Do we have the r value? Yeah. So we have 1/2 the integral of this thing, 3 sine 2 theta squared d theta, right? What are we missing? The limits of integration. If I wanted the area of just this petal, what's the lowest, what's the starting theta value and what's the end theta value? 0. 0 is the starting, what's the end? Pi over 2. Be very, very careful about this though. Be very, very, very careful about this. Are we sure it's pi over 2? When this point starts, it starts here, right? What's the r value when you're at the origin? 0. And when you get back to the origin, what is it? 0. So what's sine of 0? 0. When you plug in pi over 2 into this, you get sine of 2 times pi over 2. It's the sine of pi. What's the sine of pi? 0. So is it, are we back to where we started? Is that always going to be the case? Be very careful. The easiest, simplest, most common mistakes on these is that people fly through it, they write the wrong limits of integration, and then they're very sad. Is this an easy to integrate by hand integral?
Really?
No, the sine squared. You don't like integrating sine squared. Like, no, you're like, yes, I'm confident in my... I don't want to do that. Okay. Just like with parametric equations, you will frequently get integrals where you can write them, but then what will you use to solve them? You'll commonly use your calculator. These are the very common write but do not solve and find the answer on the AP test kind of questions. Does this make sense, everybody? So if you take anything away from this, actually two things. One, what's the area of a sector? 1/2 r squared theta, right? And be super mindful of these. Are we okay with that? Last thing that's I think is relatively straightforward, and I think you'll agree with me because it's really something you've seen before, just with different letters now. Hey, what's the first derivative going to be? What's dy dx going to be equal to if you have things written in polar land? dy d theta over dx d theta. Yay! All right. Okay. What about arc length? Hey, does that look familiar? Pythagorean theorem strikes again, right? Is this functionally identical to the parametric equation for arc length and parametric? It's functionally identical. You have horizontal and you have yay dx because you can write x in terms of theta, you can write y in terms of theta, and then you can just do the exact same thing. Nothing's changed. As we move into multivariable, which will happen in after we get back, basically when you go to multivariable, only two things can happen in my opinion. One, things are just direct extensions of things you've done before. Is this a direct extension of what you've done before? Yes. It's nothing really new. The other thing that can happen when we get to multivariable, just to give you a preview, new things can start happening that you haven't seen before, which is what I really like. Okay, get out of here.